is the Honors Chemistry section 19.4 lesson video. I'm going to try to attempt to cram it all into one lesson video, so I'm going to go really fast, but if I realize it's taking too long, I'll cut it into two parts. As always, if you want all my videos in one place, just subscribe to my channel. So let's get started, and like I said, I'm going to go fast because it's a video, so you can rewind it and watch it as many times as you need to. So in section 19.4, we talk about neutralizations and titrations, because titrations usually involve a neutralization or at least some pH change. So a neutralization reaction is a reaction between an acid and a base that forms a water and a salt. Now, a salt is a category of compounds. It's any compound formed from the cation of a base and an anion of an acid. So it's not necessarily NaCl. And so you can see, here's your acid with the H+, your base with the OH-. The H+ and OH- go to make water, and so what's left over is the Na and the Cl to make the salt. Here we have H2SO4 and KOH, so notice I ended up having to balance, so that way we'll have two OHs with two H's to make water. So my H+ and OH- make water, and my K and SO4 are left over as my salt. So you've got to remember, when you're making a compound, you've got to balance charges, and you need to remember to balance the whole reaction. So let's look at a couple of these. So it says, write the balanced equation for the reaction between aqueous solutions of acetic acid and barium hydroxide. Now here they've given me this formula for acetic acid, which is more of the organic look. You can also use HC2H3O2 as your formula. That's fine, it doesn't matter. I'll use this one though because that's the one they give us in the problem. So we have our acetic acid and we are mixing it with barium hydroxide. So barium has a +2 charge, hydroxide has a -1 charge, so of course I would need a 2 there. Okay, so +2 - 1 means I need 2 OHs. So our reaction, of course, means our H and our OH are going to make water. So I get H2O, and then our Ba and our acetate are going to bond. So that's Ba with a +2 charge, and acetate with a -1 charge. So of course I'm going to need 2 acetates. Here, I'll put our charges up for us. Although remember, the charges aren't really there once it's bonded. Alright, so last step is we've got to balance to make sure everything's equal. So I have 1 Ba, 1 Ba. I have 2 acetates over here, so I'm going to put a 2 here. So now I have 2 acetates. And then I have 4 hydrogens. So everybody see how there's 2 here, 2 here, which is 4. So I need a 2 here. So now I have 4 hydrogens. And then 2 oxygens and 2 oxygens, because of course I counted these oxygens and hydrogens as the acetate. Alright, so then it says write the net ionic equation for this reaction. So this is where you got to be careful. You've got to look at whether things are strong or weak. Strong acids and bases, when they're aqueous, they will fully break up. So when we write the net ionic equation, we write it in its broken up form. Weak acids and weak bases only partially ionize, so when we write a net ionic equation, we keep them together. So this right here is a weak acid, so I'm just going to put Wa. So even though I'm going to list it as aqueous, I'm going to keep it together. Okay, so we're going to keep this whole thing together because it's weak. That means only some of them are going to break up. This right here is a strong base. So when I say it's aqueous, that means it is really going to break apart. And then of course water is a liquid, and then if you follow your solubility rules, you'll find that that is also aqueous. Solubility rules are covered back in chapter 11, so we're not going to go back over that right now. This video is going to be really long. Alright, so remember, we got to count out our spectator ions. So if you look, this is going to all stay together. So we're not going to mess with that. Barium is aqueous here. Barium is also aqueous here. So when I write my net ionic, I'm going to get rid of barium. OH is aqueous here, but it becomes liquid water. H+ becomes liquid water, and my acetate now becomes aqueous. Okay, so normally we would assume acetate was a spectator ion, but because it is a weak acid, we assume it's going to stay together. So what I'm left with is 2CH3COOH, or 2 of my acetic acid, plus, and then remember how we pull the subscript up front, 2 OH- yields 2H2O, liquid, and then I'm going to pull that subscript up front, 2CH3COO- aqueous. So in other words, the only spectator I have in this reaction is, of course, the barium. Alright, so let's look at another one of those just to make sure you got it. Let me get on the right page in my notes, which I am now. Alright, so let's look at another one. So maybe pause the video and y'all try this one on your own, and then we'll look at it together. So it says, write a balanced equation for the reaction of carbonic acid and potassium hydroxide. So carbonic acid is H2CO3. However, I would expect you to be able to know that without me giving it to you. And potassium hydroxide. So potassium's K plus, hydroxide's OH minus. So those cancel, so we don't need any subscript. So then what's going to happen is my H and my OH are going to go to make water. And my K and my CO3 are going to bond. Well, K is plus, CO3 is minus 2, so that means I need to cross that 2 down like that. Alright, so now we got to determine the states of matter. Well, carbonic acid is a weak acid, so even though I'm going to list it as aqueous, it's going to stay together. KOH is a strong base, so when I list it as aqueous, it is going to break apart. Water, of course, is a liquid, and if you use your solubility rules, you will find that this is also aqueous because it contains an alkali note. Alright, so we got to look at what our spectators are. Okay, so this stays together on this side but breaks apart over here, so it did something. K was aqueous and is still aqueous, so I'm going to get rid of my K's. OH was by itself, but now it's water, so it did something also. So my only spectators in this case are the K, the potassium ions. So I have H2CO3 aqueous plus OH minus aqueous. And remember, when you break an ion apart, you have to put the charge. H2O liquid and CO3 minus 2 aqueous. Alright, so hopefully you got that right. So remember, if it's strong when it's aqueous, we assume it all breaks up. If it's weak when it's aqueous, most of it stays together, so you keep it together in your net ionic. Alright, so next let's talk about titration. So titration is the use of a burette to add a measured amount of a known acid or base to a measured amount of an unknown base or acid until neutralization is achieved. So you're either adding an acid to a base or a base to an acid, and you don't know something about one of them. The equivalence point of titration is when the number of moles of hydrogen ions equals the number of moles of hydroxide ions. So your H plus moles equal your OH minus moles. So it says how many moles of sulfuric acid are required to neutralize 0.5 moles of sodium hydroxide. So the important thing is you need to know the mole ratio if you're trying to do a neutralization problem. So let's write the formula. So sulfuric acid ends in acid, so it starts with H, that's H plus. Sulfuric came from sulfate, that's SO4 minus 2, so its formula is H2SO4. Sodium hydroxide, sodium is Na plus, hydroxide is OH minus, so it does not need any extra subscripts. So we're starting with 0.5 moles of sodium hydroxide. So we know that means moles of sodium hydroxide has to go on bottom, and we're trying to get to moles of H2SO4, but we don't have a reaction. Now, of course, you're more than welcome to write a reaction and balance it, but that takes too long. So what I like to do is I like to say, okay, well, I have 2 H's in my acid. I only have 1 OH in my base. 1 H can neutralize 1 OH. So if I have 2 H's and only 1 OH, I really need 2 OH's. So I'm going to put 2 here because, see, then that will give me 2 OH's to neutralize my 2 H's. So it's a 1 to 2 ratio because I need twice as much NaOH to neutralize H2SO4 since it has 2 hydrogens, since it's a diprotic acid. So then, of course, I just do 0.5 divided by 2. So that's 0.25 moles of H2SO4, which makes sense because it can only neutralize half as much because it only has 1 OH versus our acid, which has 2 H's. Alright, so let's look at a couple more of these because if you can't do this part, titrations are going to be a little tricky. And so see, you can see in my answer, I wrote the equation to figure out my mole ratio, but I just like to do it in my head when I'm actually doing it. So it says how many moles of potassium hydroxide, so potassium is K with a positive, hydroxide is OH minus, so of course it's KOH, are needed to completely neutralize 1.56 moles of phosphoric acid. So if it ends in acid, it starts with H plus. Phosphoric came from phosphate, which is PO4 minus 3, so I cross that 3 down. So if you look, we have 3 H's versus 1 OH, so hopefully you already know where that's going. So we start with our 1.56 moles of our phosphoric acid. So of course that means our moles of phosphoric acid must go on bottom, and our moles of KOH can go on top. So now we got to figure out that ratio. Well, it's 1 OH and 3 H's. So that means I need to get 3 OHs to cancel out my 3 H's. So I put my 3 with KOH to make it 3 OHs. So then I just do 1.56 times 3, which I got as 4.68 moles of KOH. Alright, so maybe pause it, try the next one, and then we'll look at it together. So it says how many moles of sodium hydroxide, so sodium's Na+, hydroxide's OH-, are required to neutralize 0.2 moles of nitric acid. So if it ends in acid, it starts with H+. Nitric came from nitrate, so it's NO3-. So in this case, there's 1 H to 1 OH. So hopefully, again, you know where this is going. So we start with our 0.2 moles of nitric acid. And so my moles of nitric acid go on bottom. My moles of NaOH go on top. Because I have 1 H and 1 OH, they already cancel. So I can put 1s with both of them. And I end up with 0.2 moles of NaOH. Like all you're trying to do is make sure you have the same amount of H's and OH's so they can cancel out and make a neutralization happen. Alright, so hopefully you got that one right, because now we're going to add a couple more steps to it. Alright, so it says how many grams of CaOH2 are needed to neutralize 25 milliliters of 1 molar HNO3. So in this case, we don't know how many moles of HNO3, but whenever you have molarity and volume, you can use the molarity formula that we learned in chapter 16. So molarity is moles per liter. And so I can solve for moles, because remember, to go from one substance to another in chemistry, you have to use mole ratio. So, of course, I multiply both sides by liters. So it's molarity times liters, and so I plug in my molarity of 0.1 times my liters, which of course I have 25 milliliters, so I know I can move that decimal over 3 places or divide by 1,000, and that'll give me 0.025 liters. And so once I multiply that, I've got 2.5 times 10 to the negative 3 moles of HNO3. Okay, so once I have moles of HNO3, I can do like we just did with the mole ratio step. So I start with my 2.5 times 10 to the negative 3 moles of HNO3. So of course that means moles of HNO3 needs to go on bottom, and moles of CaOH2 need to go on top. So here I have 1 H, but I have 2 OHs. So what's that ratio going to be? That means I'll need a 2 down here, so now I have 2 H's and a 1 up here. So once I divide that by 2, I ended up getting, oh, I didn't stop there. Sorry, I just went ahead and finished off the problem. So that will get me to moles of calcium hydroxide, because see, that'll go away. But it didn't ask me for moles. What did it ask me for? It asked me for grams. So I just went ahead and kept going. You're more than welcome to stop right there, but I mean, might as well keep going. Plus, I don't have the answer for that intermediate step, so let's just keep going. All right, so of course, I need to get to grams, so I do molar mass. So 1 mole of CaOH2 has a molar mass of 74 grams. And so then I made it from moles to grams. And so once I multiply and then divide by 2, I got 0.0925 grams of CaOH2. So see, the additional steps that we had on this one was first we had to figure out moles using the molarity formula, and then we had to change to grams instead of just doing the mole ratio step. All right, so you just got to be aware that, remember, every chemistry problem can be different. So there's always little tricks where we like to, you know, use things from other chapters to make a question a little more difficult. All right, so maybe pause and try these, and then we'll look at them together. So it says, how many grams of NaOH are needed to neutralize 20 milliliters of 0.15 molar H2SO4 solution? Okay, so again, I don't know moles, but I can use my molarity formula. So molarity is moles per liter. So if I'm solving for moles, it's molarity times liters. So I do my 0.15 molarity times, remember, divide this number by 1,000 or move your decimal 3 places, 0.02 liters. And so when I solve for that, I got, let me make sure I'm looking at the right number here, 3 times 10 to the negative 3 moles of H2SO4. Okay, but we're trying to get from H2SO4 to NaOH. So that's where I need to use my mole ratio. So 3 times 10 to the negative 3 moles of H2SO4. So I know moles of H2SO4 have to go on bottom, and I'm trying to get to moles of NaOH, so I have to figure out that mole ratio. Well, I have 2 H's and 1 OH, so I need a 2 here to have 2 OH's and a 1 here. But let's not stop there because it doesn't ask for moles of NaOH, it asks for grams. So I'll just do one more step and I'll use my mole ratio, not mole ratio, I'll use my molar mass. So when I add up NaOH off the periodic table, I got 40 grams per mole. And so then when I multiply it across the top, I ended up getting 0.24 grams NaOH. So hopefully you got that one right. All right, if you haven't paused yet and tried one, try the next one on your own, because the next one's a little different, so you never know, you might get it right. So it says, how many liters of 0.5 molar HCl are needed to react completely with 0.1 moles of PbNO3 forming a precipitate of PbCl2? All right, so we know we're starting with moles of PbNO3 and we are trying to get to our HCl. So let's start, of course, with our mole ratio. Okay, so I'm starting with my 0.1 moles of PbNO3. All right, and so I know moles of PbNO3 are going to go on bottom, and my moles of HCl are going to go on top. And so one thing you need to realize about this is we're forming PbCl2. Okay, it's a precipitation reaction. We're forming a precipitate of PbCl2. So in other words, what we have is we have a Pb and 2 chlorides forming PbCl2 solid. That's what's happening in this reaction. This one isn't really a neutralization reaction, but of course it ends up working the same way. Okay, so the thing we have to keep in mind though is how many Cls do we need for this reaction to happen? We need 2 of them. Okay, so that's where I get my mole ratio on this one. That's the important thing that you need to realize, is on this one, writing a reaction helps. Because since we know that's what we're forming, we know we need twice as much chloride as we do Pb to begin with. All right, so once I solved that, I got 0.2 moles of HCl. All right, so I took my 0.1, multiplied by 2, got 0.2 moles HCl. All right, so now that I have my moles of HCl and I have my molarity of HCl, I just need to figure out my liters. All right, so this is where we can use molarity equals moles per liter. That I'm solving for liters, so when we rearrange this, because of time's sake, I'm not going to show you how to rearrange. Hopefully you know that from my other videos. It's moles over molarity. So I do my 0.2 moles of HCl over the molarity they gave me, 0.5 molarity. All right, now moles over molarity. Remember, molarity is moles per liter, so your moles will cancel and you'll be left with liters. So once I do 0.2 divided by 0.5, whoops, I think I wrote a typo on my paper, so let me do this in the calculator real quick. My batteries are low. Thank you for letting me know. 0.2 divided by 0.5. So I get 0.4, and my unit is liters. All right, I'm sorry about my calculation. I realized I wrote a 2 instead of a 0.2, so I knew it probably wasn't going to go well from there. All right, so hopefully you got that right. This one was tricky because, like I said, you really had to think about that precipitate reaction because it wasn't a normal neutralization one. All right, so let's move on and look at a couple more titrations. And hopefully this video won't be too incredibly long. If I keep making mistakes on my paper, it's going to just make it that much longer. All right, so we've already talked about the equivalence point of a titration. It's when your moles of H plus equal your moles of OH minus. Well, there's also something called the end point in a titration, and that is the point at which your indicator changes color. And if you're trying to do neutralization, of course, you want your indicator to change color at the pH you want. Okay, so it's best when the end point corresponds to the equivalence point. The usual indicator that's used in titrations is phenolphthalein because it goes from clear to pink. So there's no question about when it's changed color. It's either clear or it's not clear. It doesn't have to go through shades of color to where you're not sure, like, has it officially changed colors yet, or is it still in an intermediate? So phenolphthalein is usually the indicator you'll use in a titration. Of course, it depends on what pH you're at, though. So let's look at a sample one together. So it says a 25 milliliter solution of sulfuric acid is completely neutralized by 18 milliliters of 1 molar NaOH. What is the concentration of H2SO4 solution? Okay, so y'all, these follow 3 steps. You do a molarity equals moles per liter. you do a mole ratio, and then you do a molarity equals moles per liter again. Okay, so remember, to get to mole ratio, we have to have moles. So, my NaOH, I know the volume, and I know the molarity. So I can solve for moles. Remember, moles equals molarity times liters. So my molarity is 1. And remember, don't forget to change milliliters to liters, so it's 0.018 liters. So that gives me 0.018 moles of NaOH. Once we have our moles, we can do our mole ratio like we just learned. So 0.018 moles of NaOH. And we're trying to get to H2SO4. So I need moles of NaOH on bottom. I need my moles of H2SO4 on top. So I got to figure out my mole ratio. Well, I have one OH and two H's. So I need a 2 here and a 1 here. So once I divide, I get 0.009 moles of NaOH. So now that I know moles of NaOH, I can finish the problem. So it says a 25, sorry, this isn't even NaOH, this is H2SO4. Well, probably would help if I had the right substance because our moles of NaOH cancel. So I have my moles of H2SO4 and I have my volume of H2SO4, so I can plug in and solve for molarity. So I'll put my 0.009 moles on top. Don't forget to change this to liters, so 0.025 liters on bottom. And so once I solved, I ended up getting 0.36, and then of course for concentration, my unit is molarity. Alright, so that is the normal steps of a titration problem like this, where you have strong acid, strong base. Alright, so let's look at a couple more. Woo, I'm taking up a lot of time. Alright. So, maybe watch one more before you want to try one, so let's look at this one together. So it says, how many milliliters of 0.45 molar HCl will neutralize 25 milliliters of 1 molar KOH? So remember, first I know my molarity and my volume of KOH. So remember, molarity is moles per liter. But I can solve for moles by doing molarity times liters. So my molarity is 1. My liters is 0.025. Don't forget to change it to liters. So that gives me 0.025 moles of KOH. Well, I'm just going to continue right here. So we're trying to get to HCl, so our next step is that mole ratio. So I need moles of KOH on bottom. I need moles of HCl on top. Well, I have one OH and one H, so it's just 1 to 1. So I'm going to get 0.025 moles, running out of room, of HCl. So in this case, our moles of acid and base are actually equal because they both have one H and one OH. So now I have moles. It says how many milliliters of 0.5 molar HCl. So in other words, I need to solve for liters. So if I solve for liters, it's moles over molarity. So my moles is 0.025 moles, and my molarity for HCl is 0.45. So once I divide and solve that, I end up with, if I could find my spot, there it is, 0.056, but my unit here is going to be liters. But what did they ask me for? Well, they asked me for milliliters, so I'm going to have to take my decimal and move it over 3 places or multiply by 1,000, and that gives me 56 milliliters. Alright, so now that you've seen 2 of them, maybe try this one on your own. So just pause the video, try it, and then we'll look at it together. So it says, what is the molarity of H3PO4 if 15 milliliters is completely neutralized by 38.5 milliliters of 0.15 molar NaOH? So again, I know the volume and molarity of NaOH, so I can get my moles. Remember, y'all, when in doubt in chemistry, just try to do something with moles. You know, once you hit stoichiometry, that's all we're trying to get after. Alright, so my molarity is 0.15. I multiply by my liters, which I will change to 0.0385 liters. And so once I solve that, I end up getting 5.78 times 10 to the negative 3 moles of NaOH. Alright, so once I have moles of NaOH, I can get to moles of H3PO4 using our mole ratio. So I start with my 5.78 times 10 to the negative 3 moles of NaOH. So of course, moles of NaOH go on bottom, moles of H3PO4 go on top, And so I have to look at that ratio. I have 1 OH and 3 H's, so I need 3 OH's, like that. And so then once I divide by 3, I ended up getting 0.00193 moles of H3PO4. Ooh, I'm running out of room here. All right, and so then the last step is we're looking for molarity. Well, we know moles and we know volume, 15 milliliters. So molarity is moles per liter. So I just did my moles, 0.00193 moles, divided by my 15 milliliters, but I changed that to liters, so 0.015 liters. And so once I solve, I get 0.31, that doesn't say 31, 0.13, and my unit is molarity. All right, again, if I'm going fast, it's because of time's sake. I didn't want this video to be 5 hours long. But you can always rewind it, or like put it in slow motion, or whatever you need to do. All right, so hopefully you got this. So let's go ahead and finish up this section. Oh my gosh, more sample exercises. All right, we'll make it. So how many grams of chloride ions are in the sample of water if 20 milliliters of 0.1 molar Ag plus is needed to react with all the chloride in the sample? And here is our reaction. So see, this one is going to be similar to the one we just did with the PbCl2 precipitate. All right, so our first step is we know molarity of Ag plus and we know milliliters. So of course we know molarity equals moles per liter. So we need to solve for moles. So it's molarity times liters. So my molarity is 0.1 molar times, I'm going to change that to 0.0202 liters. And so when I solved that, I ended up with 2.02 times 10 to the negative 3 moles, and that's of course of Ag plus. All right. Once I know moles of Ag plus, I need to get 2 moles of Cl minus. Now, if you look, it is clearly a what stoichiometry? It's a 1-to-1. Okay, so I'm going to write it, but on my notes, like I just kind of put that it was equal to the chloride ion concentration, number of moles. But I'll write it out just, for y'all's sake. So I realized it was 1-to-1 because of the stoichiometry. They gave me the reaction, so I can clearly see that it's 1-to-1. All right, so I got my moles of Ag. I figured out how many moles of Cl. And so then the thing is, though, it just asked for grams. So I just need to start with my moles, which we decided was 2.02 times 10 to the negative 3 moles of Cl minus, and I just need to change it to grams. So 1 mole of Cl minus, of course, just equals the molar mass of a chlorine atom, and that's 35 grams approximately. And so then once I multiplied, I got 0.071 grams of chloride. All right, so this one just had the one little twist of the fact that it was an ion, but you still follow the same parts off the periodic table. All right, it says if the sample has a mass of 10 grams, what percent Cl minus does it contain? Okay, so we know we have this much Cl minus, and we know that we have a total mass of 10 grams. So how do we do that? Of course, we just divide. So 0.071 grams of Cl minus over 10 grams total. Here, I'll just put total down here. And then, of course, to make it a percentage, we do times 100. And so then when I solved, I got 0.71%. Like that. Okay, so don't let an easy question like this throw you off. All right, you know how to do percentage. It's part over a whole times 100. All right, so hopefully you got that one. And hopefully this video will end at some point. I have no idea how many more slides we have to go. I'll just keep clicking until we get to the end. All right, so you try this one. Maybe pause it. Don't let this long reaction scare you. Okay, it's going to be similar to the previous one. All right, so pause it, try it, and let's look at it together. So it says a solution that contains iron is titrated with 47.2 milliliters of 0.0224 molar permanganate. How many moles of permanganate were added to the solution? All right, so we know the volume and we know the molarity. We're just looking for moles of permanganate. So this is a super easy one. All right, so molarity equals moles per liter. So moles equals molarity times liters. So I do my molarity, 0.0224, times my liters, which I'm going to change that to 0.0472. And so once I solved that, I got 1.06 times 10 to the negative 3 moles of permanganate. So this one, it didn't even make us use any of the other parts of the equation yet. Okay, the first one just said how many moles. There's how many moles. Then it says how many moles of Fe with a positive 2 charge, or iron ion, were in the sample. Okay, so if we look, there's 1 permanganate to 5 iron ions. Okay, so we start with our moles that we have here. So I'm going to start with my 1.06 times 10 to the negative 3 moles of my permanganate. So of course moles of permanganate go on bottom, so I do 1 mole of permanganate because that's what I get from the stoichiometry in my reaction, equals 5 moles of Fe2+. And since it just asked for moles, I can just stop here and solve. So once I multiply by 5, I got 5.29 times 10 to the negative 3 moles of Fe with a 2+ charge. Okay, so this one they just kind of broke it up into 2 different parts for us. All right, so hopefully you got that one right. Oh, well that was weird. They came up backwards. Oh, there's more parts. All right, so it says how many grams of iron were in the sample. Where in the previous question we just figured out how many moles, so clearly we can just change grams to moles. So I'm going to write what we got. So on our previous slide we just got this as our answer. So all we need to do is do molar mass. So 1 mole of Fe with a 2+ equals, of course, 56 grams. That just comes from the periodic table. And so once I multiply by 56, I get whoops, I didn't get 0.0. I got 0.296 grams of Fe with a 2+ charge. Okay, so that was an easy question. It just wanted me to change from moles to grams. All right, then it says, if the sample had a mass of 0.889 grams, what is the percentage of iron? So this is just like the one we just did. So we take our iron, 0.296 grams of iron, and we put it over our total, 0.889 grams total. And then to make it a percentage, we do times 100. And so once I did all that, I got about 33.3, and then my unit is percentage. See, this is one where it just broke it up into 4 different questions, just to kind of go step by step by step. So hopefully you got that right. Alright, oh my gosh, thank goodness we're to section assessment. Alright, so it says, what are the products of a reaction between an acid and a base? So, the products are always the same. You get water and a salt. Alright, water and a salt. So then it says, how many moles of HCl are required to neutralize aqueous solutions of these bases? Alright, so here we have 2 moles of NH3 and we have HCl. So if you remember, when NH3 is combined with water, you get NH4 plus and OH minus. So what that means is 1 NH3 is going to make 1 OH minus, even though it doesn't have OH minus in the formula. 1 NH3 makes 1 OH minus, and HCl has 1 H. So instead of writing it, we're just going to say, clearly that means we need the same amount of moles of HCl, because it's a 1-to-1 ratio. Alright, here we have 0.1 moles of CaOH2, so I'm just going to work off of this. So that means moles of CaOH2 goes on bottom, moles of HCl go on top, and so because I have 2 OHs, I need 2 H's, and so then I would just get 0.2 moles of HCl. Okay, so again, that's just a mole ratio problem. Alright, and then the last one, oh my gosh, the last one. We are just writing the balanced equation. So remember, when you mix an acid and a base, you are always going to make water, and then the salt will just be whatever is left over. Okay, so once I mix my H and my OH, I'm going to have K and SO4 left over. Remember, the positive one's always listed first. So K plus SO4 minus 2, so I need a 2 here. And then last step is balance. So I have 2 Ks, so I'll put a 2 here. SO4, SO4. I have 2 4 H's. See, 2 right here, so I'll put a 2 here. And then 2 O's and 2 O's. Alright, for our second one. My OH and my H make water, so I'm left with Ca and PO4, so positive one first, Ca plus 2, PO4 minus 3, so I bring down my 3 and my 2 to balance my charges. So I have 3 CAs, so I'll put a 3 here. I have 2 PO4s, so I'll put a 2 here. You gotta be careful with these hydrogens. I have 6 hydrogens plus 6 hydrogens, which is 12. So 6 times 2 gives me 12, and then I have 6 oxygens, and then right here, I have 6 oxygens. So be careful on that one with those H's and O's. All right, and the bottom one. H plus and OH minus make my water, so I'm left with Mg, which has a +2 charge, and NO3, which has a -1. So I bring my 2 down. All right, so I have 1 Mg, 2 NO3s, so I need a 2 here. That gives me 2 plus 2, which is 4 H's, so I need a 2 here, and then 2 O's and 2 O's. All right, whew, we made it. Sorry that video was so long, but hopefully now you have a better understanding of neutralization reactions and easy titration problems. They do get harder than this, by the way, if you move on. All right, so good luck if you move on.